Hydrothermal vents are located more than 2,000 meters below the surface of the sea and were only discovered to have life around 40 years ago. These deep-sea ecosystems are one of the harshest environments for life to thrive on. The vents themselves are a result of tectonic activity, as are the hydrothermal fluids they secrete. Hydrothermal fluids come from the interaction of heat from magma flowing up from between the oceanic crust and the cool deep-sea water. The fluids hydrothermal vents emit are rich in minerals and gases, including iron, copper, zinc sulfides, sulfur gases, methane, and carbon dioxide. Due to these chemicals in the hydrothermal fluids, the environment is incredibly acidic, sitting at the 2 to 4 on the pH scale. For reference, lemon juice has a pH of 2 to 3. If this wasn't hostile enough, the vents reach temperatures upwards of 150 degrees Celsius or 302 degrees Fahrenheit when fluids are being expelled, and sit at an ambient 60 degrees Celsius. So basically imagine trying to survive in a 302 degree Fahrenheit glass of lemonade. However, despite this, many geochemical niches are created for the microflora that live there. The autotrophs of these environments are chemosynthetic bacteria called chemolithotropes, who get their name because their energy comes from chemical reactions created by the rocks some grow on and the high amount of chemical reactions surrounding the vents. One of the most interesting life forms this ecosystem has to offer is the Pompeii worm, a polychaete that lives in colonies of tubes directly on the vents. These worms live in blank chimney vents and can withstand up to 105 degrees Celsius or 221 degrees Fahrenheit. While only being 6 inches long, this worm is a very important case study in understanding how animals can adapt to living in such extreme conditions. Pompeii worms have 4 pairs of external plume-like gills that contain lamellae instead of filaments like other polychaetes. They also have a layer of bacteria on their dorsal side, which almost looks like fur. Pompeii worms' blood uses hemoglobin, which causes their red appearance. Along with the hemoglobin, their blood getting pumped through a rod-shaped heart gives them their red appearance. To survive their hostile home, the Pompeii worms have to adapt. Pompeii worms' tubes are more than just their homes. They aid in temperature regulations. The worm will draw the ambient temperature seawater into their tubes when they open their gills, replacing old, warmer water with cool, more oxygen-rich water. Due to this movement, the heat created by hydrothermal fluids is passed down to the rest of the colony as well, keeping the worms on the top of the vent cooler. As you can imagine, oxygen is a limiting factor for an ecosystem like this, as hot water reaches full saturation easily and is already carrying a large amount of chemicals from the vents. To aid with this roadblock, the worms have evolved to have external gills with a larger surface area compared to the rest of their bodies. This allows them to absorb more oxygen and limit the space oxygen needs to travel to come into contact with the worm. Once the oxygen is absorbed, the worm uses it to keep its tissue alive with strong blood flow. However, due to the lack of oxygenation in the water, it's suspected that these worms may have the ability to perform anaerobic metabolic functions. The episymbiotic microflora growing on these worms is also a large part of how they thrive. Not only do these thick, hair-like layers of bacteria provide a temperature buffer, but the worms also farm the bacteria. The worms will eat both the byproduct of chemosynthesis provided by the bacteria, but if needed, the bacteria itself as well. As you can see, the hostile environment of hydrothermal vents allows only the most resilient of organisms to survive, let alone thrive. It creates astounding evolutionary adaptations like that of the Pompeii worm, and there's still so much more we don't know about the hot, acidic environment of hydrothermal vents.